Good morning, good afternoon, and good evening, wherever you are in this big wide world. Today, I'm gonna talk about a black hole model I have developed over the last summer. First of all, what is a black hole? A black hole is an object of infinite density. So basically, a mass, an arbitrary mass, collapses under its own weight to something we call as singularity, and this is encapsulated by an event horizon where nothing, not even light, can get through it after it passes it. Hence, it is black, since light cannot scatter and come to your eye for you to see it. So, why black holes are special? Because we don't understand them. As physics becomes divergent, as things turn out to be infinite, it means that we don't understand it. We don't understand what is a singularity, what it would mean physically. And it needs to obey quantum mechanics because you see, masses get smaller, like they collapse, so its density increases. But at some point, it needs to obey quantum mechanics as well, but it doesn't, so there's a problem with it. And the reason it doesn't, because quantum mechanics is fundamentally incompatible with Einstein's general theory of relativity. And the reason is quantum mechanics is a linear theory of Hilbert spaces. Einstein's theory is a nonlinear geometric theory of Riemannian surfaces. So basically, a nonlinear theory is fundamentally incompatible with a linear theory. You can think of it like that. Well, the problem isn't that simple. People have tried over the years many different approaches, loop quantum gravity, string theory, and all those sorts of exotic stuff are born out of this kind of clash between these two theories. But people haven't resolved this stuff yet, as of today. And it's very interesting because these kind of clashes of principles between different kinds of theories are the hidden gems in theoretical physics, because these signify the importance of the progress that could happen in theoretical physics. Because without these clashes, everything works perfectly. Okay, we have general relativity that explains the cosmos, we have quantum mechanics that explains microworld that just won a Nobel Prize in physics, explain the quantum tunneling in electronic devices. But of course, we need to keep testing the boundaries of different theories to come up with different concepts that would unify all those stuff. Obviously, you could come up with arguments, philosophical arguments on this kind of unification of different concepts, but again, this is how physics progresses historically as well. I don't think that it would change in the next 200 years. Maybe after we come up with this theory of quantum gravity, we would logically need to modify our conceptual understanding of reality to encapsulate different kind of approaches, but I don't know how, obviously. But yes, so what my theory does is basically to explain an alternative theory for the singularity that I was talking about. So a singularity is a collapse point. So divergent gravitational collapse happens at a single point where the mass density becomes infinite, as I told you. But this shouldn't happen. There needs to be a force that counterbalances it. And this should come from quantum mechanics, as I was telling you about. It's a huge clue because you have two theories that are so successful. Why should we come up with the third one? Maybe that's the one to go, and people are contemplating on it. For example, Gerard T. Hooft and Roger Penrose, who are eminent theoretical physicists that won Nobel Prizes, are telling that we need to come up with an alternative theory to quantum mechanics itself to explain, for example, the nature of collapse of the wave function or other things. In quantum mechanics, we don't yet to really understand. The Born rule might be a good way to go as well, the Born interpretation, you might say, where basically you take the square of the wave function, but we don't know how to do it. But if you assume that we have only two theories that exist, like quantum mechanics and general relativity, and this is the most easy, it's the easiest and most subtle way to go through in the current theoretical physics arena, then you would say that this counterbalance should come from quantum mechanics. That's why I explained you all this stuff. So what would happen? What should be the mechanism that could give a rise this kind of anti-pressure to gravitation in quantum mechanics? Well, this would come from quantum vacuum forces. You see, according to Heisenberg's uncertainty relations, where it applies to position and space, time and energy, well, that's a bit what if in physics, but anyway, so there are lots of uncertainty relations. Because of these uncertainty relations, space-time is constantly in fluctuation. So it's not a still object like in Einstein's general relativity, and this would mean a breakdown in equivalence principle of Einstein, because equivalence principle says that if you look at a certain singular space-time point, you cannot distinguish it from a curved point. So, and this is also related to the whole argument of Hilbert when he was developing Einstein's general relativity in parallel with Einstein, and that's why we also call it Einstein-Hilbert action as well. So these quantum vacuum forces is also incompatible with the equivalence principle when you think about it. Anyway, because of these quantum vacuum forces, what you have is a pressure coming from vacuum forces of quantum, and this should, in theory, counterbalance this divergent gravitational collapse, and that's what I propose in the paper. So instead of like this point of singular density that is infinite, you have a finite radius core. And this finite radius core is constantly moving, it's oscillating, it needs to be adiabatic. If it's not adiabatic, it is not natural, so you cannot obtain that particular solution through my theory. So it needs to be adiabatic. And when I was developing in the summer, I thought it being adiabatic makes complete sense. Why? Because it's quantum, you see, as I was telling you about. Quantum mechanics by itself fluctuates all the time. The vacuum fluctuates, your solutions fluctuate, your energy levels fluctuate, everything fluctuates. And if this theory is consistent with general relativity, you basically need to propose a system within GR that could account for this correction. So what I do is that I propose a Stravinsky-like correction in the curvature term in Einstein-Hilbert action, and this curvature term, I propose this constant that is in front of this curvature term, alpha, is basically the coupling term that is coming from this hidden theory of quantum gravity that we don't know yet about. But if this holds, I propose, there needs to be a finite radius of a black hole, so it needs to collapse into a core. And as I told you, this is an oscillating core. This is very interesting. So, but obviously, if you are a real physicist, if you are the real deal, you would say to me, well, Eren, this isn't physics. You are talking about a singularity here. We cannot observe this ever. Because if my friend falls into a black hole, according to GR, it can't get out. Any information my friend sends me can't get out. So how can we test your theory? Well, it's a good question. And the reason that we can test my theory is that if a divergent collapse never happens in GR, what would this mean is that this bonus structure that comes with it, the event horizon, doesn't happen as well. What would this mean? What is an event horizon? Technically, an event horizon is a switch of the signature of time and space component of your metric. So if the switch never happens, your your time component that we call as lapse function, that also encapsulates your Schwarzschild radius of a black hole, never becomes zero. So you never obtain a black hole, a real black hole. Instead, it would approach to the Schwarzschild solution. Because you see, when you propose a new theory to a theory that already works well, like Einstein did to Newton, because when we wrote Newton's equations, it worked very well, you see. We sent our astronauts in 1969 to the moon using Newtonian laws. So when Einstein developed his theory, he looked at extremal points. So he looked at Mercury, because Mercury is close to Sun, so it has the strongest gravitational pull among all the planets. So that's where the perihelion, like there's the shift of the perihelion of the Mercury that isn't accounted in Newtonian mechanics. That's what was the first series prediction of Einstein was when he developed his theory. And this is similar to that, because you see, when you propose a correction to a Schwarzschild radius, what you need to have is something that looks similar to a Schwarzschild radius at certain limit, but you would propose a correction to it, and that's exactly what I try to do. Because instead of this switch, this zero at your lapse function, what you have is a global minima that never becomes zero. And what would this mean? A global minima means that there isn't a definite point that you would define to be a two-dimensional or three-dimensional hypersurface that would encapsulate this difference between anti-causal and causal structures of the Penrose diagram that is formed by your black hole, but instead what you have is a causal structure all the time. So you never have an event horizon in that sense, but it has a minima, and the meaning of this minima is that it has a stable bound. So instead of this line, you have a final tick wall. And because of this wall, by the way, I call this fine tick wall Lamarina. It is a Turkish Cypriot term for metal covering that my ancestors used in Cyprus in our homes. So this Lamarina structure has a finite wall, finite radii, okay? And because of this, there's a maximum power that could be extracted from this cosmological object. And this was unknown previously, you see. Freeman Dyson in 1960s, in his essay, that was very famous back then, proposed, using a dimensional argument, a maximum power bound that could be extracted from a black hole or any gravitational system. And LIGO results in Caltech and simulation results break down at certain points, because, like, think about it, two black holes collapsing to each other, they emit a gravitational radiation, and you have no theory that would explain the maximum power, the gravitational power that is in these gravitational waves that could be extracted from these two gravitational bodies united to each other. And this theory, because it has a finite radius wall, could predict that maximum power bound. That's a novelty, I think, about this approach. Because if you don't have anything that would justify your approach, that is testable about your approach, you shouldn't talk about it, because it is not physics, it is metaphysics. And the another thing that is interesting about this theory is that, well, Hawking radiation, as you probably know, is obtained at the event horizon of a black hole. Basically, you see an additional flux, a particle flux, that is coming out of a black hole, hence the black hole explosion, as Hawking contemplated in his initial article in 1973, I believe. So, again, if you are proposing a correction to this event horizon, and we are calling it Lamarina, this finite wall, it also needs to predict some corrections to it, and it does. Well, what are the chances in my lifetime that we go near a black hole? It's very slim, but we have some analogs of black holes that are proposed in various places that could also explain this kind of phenomena. So one might maybe try to distinguish Hawking radiation classically and this Hawking radiation type thing that is coming out of my theory. So yeah, this was my theory. I hope you enjoyed it. Thank you.